Today we're going to learn about inductors. My name is Vivek Subramanian.
And I'm Michelle Maharbis. Let's get started. So what's inductance? Inductance is a fundamental property of circuits, just like capacitance. Capacitors, if you'll recall, store energy in the form of an electric field, and that arises because we separated charge on two different plates across the dielectric, and it gave rise to a potential. So it relates charge to potential. Inductance relates the flow of current through wires and the magnetic fields that they give rise to. And energy in an inductor is stored in a magnetic field, just like energy is stored in an electric field in a capacitor. Okay? Now, any wire anywhere when it runs a current will give rise to a magnetic field when and some sort of inductance. But if we're trying to make a pretty good inductor, we'll do something like what's drawn here. And what we've done here is we've taken a wire and we've curled it all around, sort of like a corkscrew, just going all around this core, okay, this solenoid. And it doesn't really matter for our purposes right now what this core is made of, but what does matter is that this current gives rise to a field, and you can see that it all crowds in the center, it all points up, is roughly parallel right in the center, and then it'll kind of open out on the outside, okay? Now, this setup shows you that this current flow gives rise to a magnetic field. There's energy stored in that field. And that's a fairly straightforward cartoon for an inductor.
So if I understand correctly, I mean, as you told me earlier, an isolated straight wire would have a magnetic field. And here, because of the way these are structured, where they're wiring around each other like that, the magnetic fields sort of fold in on themselves, and you get these concentric rings, so to speak.
Mm-hmm. Yeah, and for every turn, we sort of get an increase in the inductance, right? You're sort of building the total field that each loop is contributing to the center, if you want to think about it that way. Now, the last little bit I want to tell you before kind of Vivek goes into this with a little bit of math is that because the current gives rise to a field, and the field itself can interact with the charges on the current, on the wire, right, can interact with the current, changes in that current, okay, will meet with some sort of effect from the magnetic field itself. In other words, I can run a DC current, and that's okay, it'll give rise to something, but when I attempt to change it, when I DI/dt, when I try to, when I tend to change what that current is, I'll see that a potential develops between the two terminals that are trying to force that current. And that's the basis of the expression you're about to see that relates current and voltage in an inductor.
So having understood qualitatively how inductors work, let's work through the math now. Now, as Michelle told you, inductors store energy in the form of a magnetic field. So what these describe is the interaction between current and voltage that's described by a magnetic field. Now, specifically, that relationship takes a form that's analogous to the form that we saw in capacitors, except now, instead of having a relationship between current and voltage where the current is a differential of the voltage, here the voltage is a differential of the current. Specifically, the voltage that appears across an inductor is proportional to the rate of change of current. This is exactly analogous to the intuitive explanation that Michel gave you, where he said that the change in current is fought by the magnetic field, causing a voltage to be produced. Right. So you see that here, V is equal to L times di/dt. Given this differential form, we can then integrate to find the relationship between current and voltage, and we can find that the current then is the integral of the voltage. So that's just integrating this differential equation right over here. We can then put those together, and we can find the work, or the energy that's delivered into the system. This will again be analogous to the capacitor formalism, so we won't rederive it for you, but it works out to be half Li squared. And of course you know how to calculate that because the power is just V times I, and then you're going to integrate with respect to time to find the energy. Mm-hmm. Okay, so this is what we have. Now let's think about what this means. We've said that this resistance to change in current caused by the magnetic field is only responding to changes in current.
Okay.
So if the current wasn't changing, what do you think this inductor will look like then?
So if it's not changing, then there must not be a voltage drop, right? Because the IDT is 0, V must be 0.
Right.
Which means that for a non-changing current, it looks like a short circuit.
That's exactly right. In fact, that's exactly the case. At DC, an inductor looks like a short circuit. And you came to it mathematically because you said di dt is 0, so V is 0. Intuitively, the reason for that is the magnetic field is fighting changes in current. DC, the magnetic field doesn't have anything to fight.
And this actually is kind of nice because, I mean, we said an inductor was a wire, right? So essentially it is a short circuit.
That's right. An inductor looks like a wire in the DC case.
Right.
Okay? Now, what that means is, of course, really if you look at the function of an inductor and how it works, it basically fights changes. And so in other words, the current through a conductor must be continuous. Abrupt changes are not possible because then you get an infinite fight because di dt will go to infinity.
And this is the kind of thing that students get flipped all the time. So current through an inductor must be continuous, no abrupt change. And
Right.
remember that for a capacitor, voltage through a capacitor must be continuous, no abrupt change. The other two do not have that constraint. So voltage on an inductor does not have the constraint that current does. You can abruptly change a voltage across an inductor.
Correct. And oppositely for a capacitor.
Correct.
Now, Michelle gave you another little gem of information, which was related to the way we wire up inductors. And specifically, you probably remember, since I know you all hold his comments with bated breath, you remember that he actually said that when you loop these on each other, the more turns you have, the more inductance you build up because these magnetic fields sort of reinforce themselves. And that makes sense because if you look at the equation, this is an equation that describes the inductance of a particular coiled inductor, and the inductance goes as the square of the number of turns because N is the number of turns. Mu and L are related. Mu is related to the material properties of the system. L and A are geometry parameters.
So speaking of gems of information, I actually hope I didn't say that the magnetic field increased linearly with N in the last slide. Hopefully I did say N squared or said nothing. Anyway,
I think you were smart enough. You didn't say.
Probably. So it's N squared, people. Okay.
So, yeah, that's right. So anyway, the point is this sort of lays out the groundwork for you to consider how to use inductors in circuits. A, you know how to construct inductors, and B, you know how they are affected by changes in current. So now, having done this, it probably makes sense for us to look at one of those changing current scenarios and figure out what the current voltage relationships are.
Cool.
Michelle?
And this will be similar to what we did with a capacitor. I think you're seeing that for this module we're going much quicker because it's all very dual. So let's take an example. In this case we'll make it a little more complicated than we did for the capacitor response slide. So here we have a current that we're going to run through an inductor. And this current is going to take this form. And we're not quite saying why that's the case. We'll get to these kind of things a little bit later, but this is going to be the form of the current going through the inductor.
Wait, I recognize this form. I think we talked about this when we talked about non-periodic waveforms.
We did.
So it appears to have a sinusoid over here, but in addition, there's an exponential decay over here. So it's a decaying sinusoid.
Yeah, that's exactly right. Or a damped sinusoid, decaying sinusoid is exactly right. Basically, it's kind of a neat example of how you can take two of these things and put them together. This is going to oscillate, and then the amplitude, you can think of this as being the amplitude of this thing, and that amplitude is decaying with time as an exponential. So that's exactly right. So let's say that we state that that's the case. So the current through this inductor, you can see it's I of t going through it, gives rise to a V of t. The current looks like this, as given by this expression. The sinusoidal part means that it goes up and down, it oscillates, but the decaying part means that it's got an envelope to it that's increasingly constraining and diminishing the total amplitude. So you see it goes up, there's a maximum around here, there's a zero crossing around 2, and then there's another zero crossing around 4, and so on.
I see. So here what's happening is with each successive half cycle, the amplitude keeps dropping because of that decay on the exponential.
Because of this part. That's right. It's pretty neat. So now we can use this expression we've got from the last slide, V equals L di dt, so the voltage across the inductor is L times the derivative of the current through the inductor, to come up with V. So here's a plot of voltage, and all we've done is multiplied the inductance times di dt, okay? And on the side here, it's done for you sort of mathematically, and here it's done graphically. And what you see is, here's the derivative. Now notice, right at 0, the derivative is very high. So you start out at high value, but of course it starts leveling off, and at the peak here, the derivative is 0 because it's horizontal before it starts to drop, and that's where you get your zero crossing.
I see. Now so that's coming from the shape of the sinusoid. The sinusoids are very steep, close to 0, and then as they approach the peak, they start leveling off.
Yeah,
makes sense.
Exactly right. And so that then you get what you expect, which is you get this follower. Now you might not be able to tell, but you can see that this, just like the capacitor, this is also 90 degrees out of phase, just in the other direction.
Yep, you're right. And you can kind of tell because it starts at a high value and hits 0 when the sinusoid hits the high value over there.
High value, exactly right. And just as we did with the capacitor, we can do P equals IV. So we multiply these two to get power, and you'll notice that Well, Vivek, what do you notice? What's interesting about the power? I've been talking too much, I think.
Okay, well, what's interesting about the power is I see that it seems to have zero crossings at twice the rate that the voltage and current curves do. In other words, I have 2 zero crossings in the time in which the voltage and current have 1 zero crossing each.
Yeah, I mean, that's approximately true, right? Because you've got this other component. But yeah, and so you can see that it's faster, certainly faster than these two things. And here it's done for you. This LDIDT is done if you want to play around with some numbers. You can see that we've chosen, I believe, a 50 millihenry inductor, and you can kind of see what all these numbers look like, so you can do them yourself. Okay, so hopefully that makes some sense. And we'll wrap up just like we did last time with a little discussion of inductors in parallel and in series.
Okay, now here we'll move more quickly because you've already learned how to put this together. If we consider a series combination, we would figure these out using a KVL because we've got a loop that's set up. The voltage across the entire string of inductors is going to be the sum of the individual voltages. We then substitute in the V is equal to L di dt for each of the individual inductors. You isolate them out, and what you find is that the voltage across the string is going to be L1 plus L2 plus L3 times di dt. Remember, because they're in series, the current has to be continuous. In other words, the di dt is the same for all 3 inductors. Now, what does this say? This says then that for an equivalent single inductor that I use to represent these 3 inductors in series, the equivalent inductor would have a value L equivalent is equal to the sum of the individual inductances L1, L2, L3. So this is exactly analogous to resistors, where series resistors are added. This is unlike capacitors, where parallel capacitors were added.
Fair enough.
And maybe, Michelle, you can pull this to a close by covering parallel.
Oh, sure. So here we're going to do the same as we did for pretty much all these elements in parallel. Notice that IS, the current coming in, is going to be split down to 3 branches, I1, I2, I3. The voltage is the same across all of the conductors, okay? And we thought we'd leave it for you right at the end to following the same thing that we did with resistors, follow the exact same procedure you did with resistors, except instead of Ohm's law, V equals IR, you have V equals L di dt for the expression, and you should find that inductors in parallel add in the same way resistors do. In other words, that 1 over L1 plus 1 over L2 plus 1 over L3, and you take the reciprocal, that gives you L equivalent.
So again, it's just the reciprocal of the sum of the reciprocals, just as it was in resistors.
Yeah. So the goal here is to let you kind of do this on your own, make sure you work this out. So I think this wraps up capacitors and inductors, and we're going to see you pretty soon as we start to do our first order circuits. Thanks.